Okay, looks like everybody is seated and ready and set with all their pizza and drinks. And I hope you've not just come for the pizza, because the talk is also going to be really great. So the pizza is good, but I know the talk is going to be really great. So hey, thanks everyone, all of you, for coming here for the meetup. And I hope it wasn't too much trouble finding the place. So hope you, and not too much traffic. So welcome our guest speakers. So today we have here Silver Spring Networks team, Greg and Darren, and they have created this IoT platform called the SilverLink Big Data platform, which uses Apache Apex as its foundation. And today they will talk about their IoT use case and the platform that they have created. So really thrilled to have you guys here and hear what you guys have to share about this. So just a few housekeeping things. If you have any questions, best keep it till the end of the talk. But if it's really compelling, absolutely go ahead and ask the question. But just raise your hand so we can pass you the mic, because there's also a remote audience. There's some folks who are joining this on the webinar, so it'll be easy for everybody to hear the question. So one of us will pass the mic to you. The restrooms are outside, and turn left outside our door if you want to take a quick restroom break. And then after the presentation, it'll be great if you can fill out the feedback forms that we have at the back there. Just give us feedback about this meetup. Tell us about what motivated you to come, or what other topics you would like to hear. Any other suggestions for future meetups, we'd love to hear from you. And of course, we have t-shirts and some stickers to give out, so make sure you collect those as you're walking out. So without further ado, would love to introduce Darren and Greg here. Greg is the product manager for the SilverLink data platform. He actually has been involved with rolling out some of the earlier projects with the SilverLink network in Copenhagen, and he's been very closely involved with the whole Smart Cities project. So delighted to have him here. And Darren, he's a software engineer, a big data software engineer at SilverLink Networks, and he's also an Apache Apex contributor, and he's been very closely involved with the development of this platform at SilverLink, Silver Spring Networks. So over to you, Darren, first. Yep. Sorry, to you, Greg, and then we'll get started. Thank you.
So thank you for the introduction. So hey everyone, my name is Greg Brosman. I'm a product manager at Silver Spring Networks, working on the SilverLink data platform with Darren here. I'll start out by giving you guys just a little overview of Silver Spring Networks, so who we are, what we do. I'll talk a little bit about the challenges that we've faced and that we've worked with our customers on, and the reasons for us trying to build out the SilverLink data platform. Talk a little bit about the journey that we've kind of undertaken in the past couple of years, and kind of set that up so that you understand what Darren has been working on behind the scenes there. So as background, so Silver Spring Networks is a provider of technology. For about 10 years, we've been selling into the utility industry. We provide a mix of hardware and software that enables utilities to manage smart grid networks. So this is stuff like smart meters and technology to manage devices that are monitoring the grid. So on the side of your house, I assume a lot of you are PGE customers. You'll likely have a smart meter there, and there'll be a little sticker that says Silver Spring Networks. And so we work closely with PGE, and we help enable the communications between PGE and that device. And there's a variety of benefits behind these smart grid networks. Stuff like automated meter readings, so rather than having to send someone out once a month to go manually collect usage information, PGE and utilities can collect that nearly in real time. Operational efficiency is a huge one. So rather than rolling out trucks every time that a utility wants to connect or disconnect power, utilities can now actually do that remotely with these two-way smart grid networks. And a big one for a lot of us, and especially for commercial customers with lots of very expensive equipment, is reducing the frequency and duration of outages. So this is really critical, is rather than having to call your utility when you notice an outage, you want your utility to find out before you do. And so that's something that we've worked out with our utilities to do, is make sure that they have the latest and greatest information out there. Just kind of a sense of scale. So we're essentially the biggest provider out there, over 20 million connected devices. And Darren will talk a little bit about the kind of big data challenge that we see coming through. But you can imagine 20 million devices creates a lot of data every minute, every hour of every day. So in the past couple of years, I mentioned we've been in this game for over 10 years now. In the past couple of years, as more and more utilities have deployed these smart grid networks, there's common themes have come up. And one of the most frequent topics that I hear about frequently is, so Silver Spring, it's great. We've got this smart grid network in place. It's working. We're automated the meter readings. We're doing remote connects and disconnects. Outages are no longer as painful. But we're kind of ready for the next step. These are big investments, and so the utilities are looking to leverage these networks for more stuff. So the kinds of stuff that utilities tell us about are, all right, if we've got a network canopy in place, what other kinds of devices can we put out there? So this is stuff like smart streetlights, connected traffic monitors, environmental sensors, public safety tools, as well as additional grid optimization and monitoring devices. So there's a variety of new devices and sensors that want to hop on these networks. This kind of gets to the second point, though, which is, all right, if I'm adding 1x, 2x, 3x the number of sensors, or I'm considering doing that, what do I actually do with all this data? These things are going to be sending me data every second, every 10 seconds. It's going to be real-time data. It's going to be batch. How do I secure this data? How do I store it down? And then the final piece there is, how do I get it to the applications that are actually going to make use of all this data? It's great to collect tons of data, but it's not really that helpful if you can't get that data to the analytics applications that are going to find the patterns, to the application, the workflow tools that are going to create an alert and dispatch a truck if necessary to go deal with a problem. So this is essentially the background of what we've heard for the past couple of years is we want to do more with our networks. There are new kinds of devices that we want to get out there. They're generating more data, but how do we actually connect this data with the applications that can make use of it? Luckily, there is a solution. Now, this is the tool that we're essentially focused on working with here. So this is the SilverLink data platform that Darren and I and the rest of the data platform team focus on. And our kind of tagline, what we think about doing every day, is seamlessly connecting applications with sensor data. We want to make this process as easy, painless, fast, reliable, secure as possible. So looking at this this chart here on the right, you'll see at the bottom layer there's a variety of devices out there. So our core focus for a long time were just the meters. This was the electrical meters, gas meters, water meters on the side of your house or in a C&I building contributing data. But I've talked a little bit about the proliferation of new devices, and so that's what I've tried to do there. Taking a step up, there's a variety of data sources that actually compile this data. So we own some of it for the network data that we collect. But there's also interesting third-party data out there, like weather information, topography information, mapping, et cetera, as well as utility or other customer data that they may collect. What we actually try and do then is to centralize all this data in one place. So rather than having it siloed across n number of databases, we're trying to collect it automatically in a single place and really do two things with that data. One is serve it up to applications on top in real time. So again, that's kind of like the workflow applications. If there's an outage, if there's an event that needs dealing with, that needs management, we want to get that event, that information to the right application as quickly as possible, and that's that kind of real-time angle there. The other piece is the more historical piece. So, for example, if a utility is dealing with a lot more renewables on the grid, if people are deploying more solar, if wind is out there, a lot of utilities these days want to understand, how does this impact the grid? I want to look at 1, 2, 3 years of data to understand how the grid appears to be changing and the implications for me. And so this is really, I need all the data that you can give me for 3 years back. So these are kind of the two major requirements that we see. And then at the very top there are the APIs. So again, one of the more painful things is hooking the data up to the applications. Custom integrations take time, they're painful, and we're trying to solve that through a layer of standard APIs at the very top. So what's next is we're focused on developing the data platform, getting that out to our core customer base, and then opening that up to a new generation of sensors and IoT devices. And part of our new initiative is something called Starfish that we've released in the past few months. And the idea here is to use our over decades worth of networking technology and open that up to a new ecosystem of sensor devices out there. So we've got a lot of expertise in networking and communications between devices and applications. We want to reach out to all the new developers out there who are focused on really cool IoT devices. So again, environmental sensors, water, food, traffic, safety, transportation, all areas that are very popular for cities these days, utilities, enterprises. And as part of this effort, we are actually kicking off a hackathon series. So we are going to be opening up both our hardware kits, so these are our NICs, our network interface cards, as well as software to connect with the data that these devices are generating. So if you're interested in Starfish, if you want to learn more, please either talk to me afterwards or find us online, ssni.com. So let me take a pause there. Again, this is a background on Silver Spring and what we do. I'll now actually transfer this over to my colleague Darren here, who's going to go into more technical detail around the data platform and how we manage the data pipeline.
Great, thanks, Greg. Can everyone hear me? So my name is Darren Nee. I'm a software engineer at Silver Spring Networks, and Greg and I work together on the SilverLink data platform. And I'm going to be telling you a little bit more about kind of the background and context for our use case of Data Torrent, and then look at one of the apps that we built, kind of walk through each of the operators and touch on some details of what they do, some of the considerations, and then share some of the hurdles that we encountered and kind of get into some of the solutions we came up with. And then feel free to ask questions as well. So the kinds of data that we work with, as Greg kind of introduced, are first off the meter reads and interval data that are coming from our smart meters. The network interface cards on these smart meters relay that back to Silver Spring Networks. So a meter read, again, being a register read, which is what utilities used to dispatch human personnel to record in order to do their billing process. Now with smart meters, they're recording as well interval data, and this enables them to do time-based billing and other use cases for managing their grids. Another type of data that we're ingesting is threshold events. These are things like alarms when a voltage exceeds a certain threshold or a temperature. Utilities are interested in knowing in advance whether or not certain components are at risk of becoming inflamed, or other kinds of situations that they may be able to proactively resolve. And lastly, device metadata. So these are things like the location and address information of a meter, or the network topology. For instance, what's the MAC ID or the NIC MAC ID, and what is the backbone infrastructure that it connects to. So the rough sketch of a data flow that we're working with is, first, NICs collect data from meters. A NIC is the networking component that acts like a radio and relays this data back to the back office of the utility on our network. So There's two ways that data gets to their back office. One is through polling. Another is it's sent asynchronously. And from there, we have agents which transfer these data elements, which are either files or JMS messages, to our data platform. At that point, we process files and messages using Data Torrent and other components, and then from there it goes out APIs and SQL. I'm going to touch briefly on some of the key qualities that we're seeking to embody with our product, one of which is security. This is absolutely critical for our customers. Our customers are utilities, municipalities. They're highly risk averse. So we provide both encryption of data at rest using symmetric keys and individual keys for each customer. We also use SSL so that data in transit is encrypted. We use Ranger and Knox as Hadoop components to enforce security within our cluster. Why is all this security important? You might wonder, what's the value of a particular voltage measurement? Well, some of this information is personally identifiable information, so PII is subject to certain laws. Utilities are bound to have certain security enforced, so we end up having to provide a high level of security, just like it was credit card data. Auditing is another aspect of this security requirement that we sometimes that we provide. So it's not enough to be secure. We actually need to prove it. We have teams that actively study our platform and applications and look for ways to improve them. We do not want. So we do not want to mix data between tenants, as would be obvious, but it's worth mentioning in a shared system. This brings us to multi-tenancy, which is another key aspect of what our platform provides. It's not something that utilities actively seek out. Obviously, in their own ideal situation, they'd each want their own clustering of machines for their data. However, the efficiencies of scale demand that we use a shared resourcing structure to host all of our customers. So it cuts costs. We have a variety of profiles of customers. Some are very big, millions of devices, say 5 million meters. Others are just getting started, just pilots, so a few meters. And so it doesn't make sense to deploy a whole Hadoop cluster for a small tenant. So that's another aspect of this multi-tenancy. We are able to centralize management, and let me move on to the next slide. I wanted to provide some numbers on scalability and just to give an idea of how big our data problem is. We're anticipating roughly 0.5 terabyte of data a day, and this is based on looking at roughly 20 kilobytes of data per meter per day, which translates to 20 gigs of data per million meters per day. And you can break it down looking at how many intervals there are. For every 15-minute intervals, there's 96 of them in a day. Supposing we have 4 channels, voltage, current, power, etc. There may be a few more. You can see that there's roughly 8 billion intervals in a day with our current number of meters. Then we're also thinking of adding sensors generally. So that's actually going to go well beyond this number once we move forwards with the Starfish platform.
There's a question.
Sure.
One more question. For security, do you have double-side authentication? So your server can authenticate the client also?
We do, yeah. High availability and disaster recovery. These are elements that many big data projects seek, and actually projects generally. I mean, this is infrastructure level data that folks will be building applications which may be critical to things that we're not aware of. It's absolutely critical that we have high availability. And so this sort of gets into a lot of the main reasons for using a Hadoop platform in general. Clustering, automated failovers, rolling upgrades. These are characteristics that are highly desirable, so I'm going to just sort of mention them and then we'll kind of move on for now. An overview of our technical architecture. So I'm going to briefly go through the technologies that we use, walk you through really quickly how this all fits together in our platform. I mentioned that the back office software that our customers have relay both files and JMS events to our data platform, which is surrounded by a firewall. They land in HDFS and Kafka. From there, we ingest them through Data Torrent and output them into Elasticsearch, OpenTSDB, and HBase, as well as and then at that point, we also asynchronously take our processed HDFS files and load data into Hive, and from there we serve. From OpenTSDB and Hive, we serve APIs in Mule and Apogee, and then Tableau is used as an interface to the Hive data, providing rich data visualizations for custom use cases. Things like showing a map view of meters and issues that are coming up, these kinds of things that utilities want to know about in their back office. Okay, so why did we choose Data Torrent? We evaluated our decision about a year and a half ago. At that point, Data Torrent was version 2.0. We looked at the management UI console. We thought that was a very big value add over Spark. We thought that would highly enable us to do a handoff to an ops team from our development team. Seemed like something that was going to allow us to get started a lot faster. So beyond that, the Malhar library of operators and being based in Java, not that these are things that Spark didn't provide, but we thought they were high quality and we were able to build apps quickly with them. So they provided a roadmap for us to get going. Very useful. I think we had our first few apps within literally a month or a month and a half, and we're moving forwards. So that's a big advantage, obviously, for a new product. Secondly, the ability to scale was demonstrated through the automatic partitioning schemes, and I don't know exactly how familiar you all are with the features of Data Torrent, but it provides a way to relatively simply decorate what's called an operator with code that enables it to partition. And this is essentially duplicating the operator across different Yarn containers, and that's the way it's scaled. So that was attractive. To kind of restate these points, these are all strengths. Operators are resilient. Data Torrent provides a way to recover from failures. So this boosts availability, which is an obvious plus. Again, it's easy to partition operators. Any Java programmer can build a simple app. We wanted to facilitate management handoff to operations, and we found it easy to detect failures with the UI. So as we continued our development process, we did encounter some focus areas that we chose to improve upon. One thing that we quickly identified was there was a lack of built-in mechanism to provide what we refer to as back pressure, which is essentially an ability to slow down the processing rate of an operator. And I'm going to come back and go into more deep detail on what I mean by that. Secondly, when an operator crashes with an out-of-memory error, Data Torrent was restoring that yarn container to the same conditions that led to that state, so that's a problem. There wasn't a good way to stop an app and save the context where you stopped. There's kind of this understanding that these applications are running continuously and kind of you want them to be always up, but in our release cycle, we extend apps and we make changes. So there are times when you have to bring down the app and bring it up again, and you want to pick up where you left off. Finally, it can be difficult to navigate the logs at times. I think the UI provides a lot of good access to them, but it's still, there's ways that it could be better. Okay. How are we doing on time? I think we're good. I'm going to walk through at this point an example of one of our Data Torrent apps. So what I'm showing here is a screenshot of the Data Torrent console while it's in operation. And briefly, the AMM is the Advanced Metering Module. That's what that stands for. This is our back office software that the customer runs, which receives all of the register reads and intervals and events. And it has it had an existing capacity to create scheduled export jobs, so to create export files. And in an effort to facilitate a simple integration with this back office software, we ingest those export files. So that's the design. You can see there's 6 operators, and I'm going to, in the next slides, go through each one. You can see in this screenshot that we're using roughly half a terabyte of resource, and we're processing about 250,000 tuples per second, which is, that's a benchmark for people to understand what it's capable of. But let me explain what that means in more detail. The input operator is scanning the last 2 days of raw HDFS directories for new files that haven't been processed. All it does is emit file names, and it's very simple, but it's too fast. This is an operator that basically it does a very simple job. The next step, we have a file reader operator, parses different types of files. It could be XML or CSV, and it emits Avro tuples. We chose to break our data apart at the level of tuples that belong to a single device. A tuple can still contain many intervals or register reads or events, but each one is unique to a device. And that said, there's still a high degree of variation in the size of a tuple, as well as input files can be quite large or very small. So this leads to sort of uneven performance in terms of the number of tuples processed by this operator. The next step is to enrich each tuple with device metadata. This is a common use case, I think, for many data ingestion apps, is to kind of embellish, decorate the tuple with extra data. we have our device metadata stored in Elasticsearch, so that creates an external dependency. Something I'd like to note, since a lot of our operators have some external dependency on another Hadoop component. One other thing to note about this operator is one Yarn container is actually more than what's needed for a single Elasticsearch client, so we use a thread pool. After being enriched, we send tuples through something called the Avro converter. Each tuple may have a different type, i.e. it can be from a different version of an XML schema or CSV schema, and so we want to normalize across all of these versions. So we have a basic data model that is, there are intervals and there are events, there are register reads. These things are basically the same, even if your XML file has a different schema version. So we normalize our tuples and then output to different kind of output operators. So this is kind of a switching operator because it also deals with a lot of object instantiation. In copying these tuples, it has a high demand on memory, and we've seen out-of-memory errors with this particular operator when you have a high throughput. Throughput being the number of tuples emitted in a window. One of the output operators is what we call the enriched persister. This writes the Avro tuples back to HDFS. And Avro is a format that requires a header in each file. So this is one of the kind of customizations that we added to the Malhar library file output operator, abstract file operator, output operator. And as well, we have a naming convention for our output files that includes the processing date and the input file name. This allows us to, if we need to do a reprocessing job. For instance, if there's some sort of operator failure in the midst of writing tuples, we can remove the output files and reprocess that file. It's not something we've had to do very often. Again, this operator has an external dependency on HDFS, which under high load can also be slow. The name node can be overburdened, and then network issues can also slow down this operator. So there are plenty of opportunities for there to be bottlenecks, and these are reasons why we, what I'm going to get to, looked into a need for back pressure. The TSDB writer, this is the operator we use to output data to HBase through what's called the OpenTSDB, which is essentially a data model API that supports interfaces to HBase. So we've embedded an instance of OpenTSDB in the operator, in this custom operator, and it experiences a bottleneck when there's a lot of new devices that are coming in. There's a need to create metrics in HBase, and this is a slow operation, as well as when there are HBase region splits, it can be very slow. So that was actually a prior version of our AMM export DAG. We've continued working with it, adding more endpoints. So one of them is a file encryptor. This relates to our need to encrypt data at rest. Another is outputting to Kafka using the Malhar Kafka output operator, which I think you guys have recently heard about. So due to the classic Yarn application solution is to spin up more containers in order to scale up. And we found that it's not so simple because of these external dependencies on Hadoop components like Elasticsearch or HBase or HDFS even that don't have the same ability to just scale in that way. And as well, that we have highly variable loads. Files can be very large, very small. Tuples can be large and small. There can be tuples coming from different types of files in a different proportion. So there's a lot of things at play, and these caused for the overall throughput through our DAGs initially to have been very variable. We'd actually end up with out-of-memory issues where operators would fail and then get into this state where they'd be persistently failing. And we realized that we needed a way to slow down the upstream operator so that we didn't cause these recurring failures and then speed it back up once things were flowing again. Dynamic throughput management is what I'm going to call that. And throughput, again, is how many tuples an operator can emit per window. So we talked to Data Torrent. We asked them what would be a good way to do that. And they introduced us to the stats listener interface. Allows us to auto-tune the throughput rate. So our first, I'm going to describe really quickly a couple implementations that we made. I think this is sort of like the key to our application being stable. The first was that we generalized a stats listener so that it could apply to any pair of logical operators. And that means that they could be partitioned or not. And the most sensible pair would be two that are connected by a stream, although that's not actually a requirement. We basically insert a counter into each operator in a strategic place. And this is a custom counter, not one of the ones that's provided by Data Torrent. And then keep track of a backlog, a measure of backlog, as well as a measure of how many tuples have been processed by the downstream operator. So the initial implementation was to scale the upstream operator's throughput by a factor, say 90% or 110%, based on whether or not the backlog at the downstream operator exceeded or a certain threshold, like say 10,000 tuples, or if it was below 100 tuples, maybe we'd increase the throughput. It didn't work totally well. It actually gave us kind of oscillating performance. Turns out that there's a lot of control theory about this. Says it's not going to work because it will never converge to a reasonable value because we were not feeding back on a derivative of the error. So that was our second implementation. Is we compute a backlog, which, for instance, it may be the difference between the number of tuples that have been emitted by the upstream operator and the number of tuples that have been fully processed by the downstream operator. Then we try to maintain a target backlog that's a multiple of the number of tuples that the downstream operator is processing. So let's say the downstream operator has processed 100 tuples in the last window, or in the last n windows. We might want to maintain a backlog for that operator of 400. In that case, let's say its backlog is currently 200. We'd want to set the throughput on the upstream operator to 200. So in any case, this model worked much better. We were able to observe much higher throughput, and we didn't find our operators crashing as much. In fact, we were able, and I'll get to the next slide, to show that we could process large data sets successfully. We did encounter a couple other nuances in this approach, which are that stats weren't reported when an operator wasn't emitting any tuples. And so we fixed that by adding a small but positive minimum throughput. So you can't completely throttle an operator. Again, there's issues with that. For instance, with the AMM export ingestion app, where you have file names being emitted in and then each file containing maybe thousands of tuples, you can see that the relationship of throughput is vastly different. You may have a very discrete level of throughput on the input operator. Say you only have one file per window is what you're targeting. That's kind of a rough measure. So we ended up going into fractional or probabilistic emission of a file name to determine whether or not we should, as a throughput management mechanism. So successes, operators didn't run out of memory and crash. The overall throughput across the DAG was much higher. We can adapt to a wide mix of loads. It's general enough, we're using it in all our apps. We ingested 4 multi-month pilot data sets successfully. We reduced the time it takes to ingest what we measure as 1 day's worth of data from 1.5 hours to 15 minutes. This is important because you want your backup, you want your data platform to be able to ingest everything in a very short period of time for a day. Otherwise, things can start you can get behind too quickly. And it's automated hands-off tuning. It's fun to watch. It's a good system. Remaining problems, it's based on tuple count. Not all tuples are the same. Some are very large, some are small. So there's still some edge cases where you can end up in an out-of-memory failure state, although it's very rare. Garbage collection remains an issue that can cause uneven performance. It can be slow to converge, and testing and debugging these kinds of models you have to have a large data set to begin with to get to the point where you can really push your system to the limit and then see what it can handle. Okay, one other kind of technical topic that I thought would be interesting for the audience is the issue of stopping DAGs. So let me go over what the problem was and some solutions that already exist. It's necessary for us to stop processing periods at some points to, for instance, upgrade the version of our Data Torrent app of our own operators and processing, for instance, to extend it with additional output operators. If you're ingesting from Kafka, if you're taking messages off a Kafka queue, you can persist the offset and then restart with that same offset once you start your new app. If you're dealing with files, a simple way not to reprocess a file is to rename it after you're done reading all the tuples from it. Then the scanner won't, if it's configured with a pattern, will not recognize that and reprocess it. So those are two techniques that we used right off, as well as we introduced what Data Torrent provides as the checkpoint listener, so that we didn't drop any tuples. What this does is enables us to wait on persisting either these Kafka offsets to Zookeeper and renaming a file until a tuple has fully transited the DAG, i.e. A file reader may have read all of the tuples from a file, and they may have been emitted from that file reader, but they haven't been actually written to HDFS. So you don't want to rename the file to .processed until all of those tuples have been written to HDFS. So this checkpoint listener provides a callback mechanism such that a file reader, for example, can sensibly commit the state to .processed. That prevents loss of data between if the DAG were to fail or be stopped in the middle. However, some tuples can be processed twice. So this can happen, for instance, if You then restart the DAG, and the tuples which hadn't been, for a file which hadn't been moved to .processed are then also re-emitted. So we looked for a cleaner way to exit processing. A simple way we came up with was to use the REST API and set a flag on an input operator to tell it to stop emitting tuples, and then just wait for the DAG to become inactive. And we've used this for the last year. It's actually a very effective mechanism. But it's not built in, so that might be something that Data Torrent considers doing. Versions, we're on Hadoop 2.3.0 and Data Torrent 3.1.1. So, any questions?
How much data are you typically processing per day, let's say? How much data are you processing?
Currently or anticipating?
Currently, let's say.
Currently, we're having relatively low loads because we're still kind of ramping up our customers, getting them integrated to our platform. So I think at this point, it's not going to be a very interesting number to you. But what we're looking at is roughly half a terabyte a day once we're fully deployed. So, yeah.
What's the rate of processing at the fastest that you can effectively handle? Like, is it like, what's the data processing speed, like a millisecond level or sub-millisecond level?
I'm not certain I understand the question. So the data processing speed is really just dependent on how much resource we allocate for the DAG. And so we've used up to, I think, about half a terabyte of RAM for our operators. And I think we did, I don't have the number off the top of my head exactly how much we're writing to HDFS and what window of time, but I think those figures are in the Data Torrent operators. They can be, yeah.
It's below millisecond level, or is it above?
Are you talking about latency between end to end?
No, the processing speed. Like, I'm trying to compare it with Spark streaming. How effectively Spark streaming can process data versus.
I don't know the comparison. My sense is it's comparable, but yeah.
So when you're renaming files from the processed to non-processed state, or vice versa,
Sure.
wouldn't it be much more efficient to keep a really small index of processed files versus changing actually every file in a large set?
Where would you keep the index? Sorry, could you say a little more about how you would do it?
Right, so instead of traversing the entire file system and renaming every file that you process, keeping a small index separately and not changing the file system, right? Just going through and reading it. You don't have to do writes to the file system. So you're going to gain some benefits if you do that.
Okay. Yeah, I mean, I think there's a lot of ways to do this. This is just one approach. So that may be a better way to do it. Any other questions? Yeah.
Most of the records are duplicate records, or at least the data is duplicates. Am I right? The duplicate in the sense the same data comes over again and again. For example, the meter ID and the MAC address, except the time, maybe the usage count, most of the data are duplicate data.
Yeah, Could you say more what you?
Okay. Every time a record comes into Silver Spring or the Spring Link, the platform that you are talking, the record consists of set of data, set of fields. Each field contains a data. For example, the time, the meter reading, the MAC address, right?
So it's all structured,
structured.
as either XML or CSV or JSON.
Exactly.
So but we transfer data in a compressed format usually. So and then we don't check for duplicates. It's something that we, I think we're just ingesting what's sent to this platform. So I think if upstream is sending duplicates, then that is a problem. Yeah.
Okay, I think I got the answer. Thank you.
Okay.
You mentioned about a container is too big for a client, so you leverage Redpool for that. So can you add more details about that? How did you use it?
Sure. When a tuple is received on the input port, we put it on a queue. We have a pool of worker threads, and when it's idle, it dequeues a certain number of tuples from that queue, and then it batches a request to Elasticsearch. It decorates each tuple with the device metadata, and then it puts it on a done queue, and then the main thread of the operator then emits the tuples from the done queue. Does that make sense?
How is it isolated within a container? So that was my question. You mentioned about within a container can be too big for so.
Oh, so
yeah.
I think the default size for a Yarn container that we're using is something 4 gigs or something like that. So I think if we were to do one transport client in each container and then scale up that way, we'd end up with so many Yarn containers it wouldn't make sense. We may as well use a thread pool within that same Elasticsearch enriched or Yarn container. Does that make sense? Yeah.
Can you talk a little bit more about multi-tenancy? What does it mean in your system, and how you handle that?
Yeah. Okay. So we have dozens of utility customers. PG&E is one of them. ComEd, FPL. I mean, we have customers around the globe. So multi-tenancy means that we are using the same Hadoop cluster to ingest and persist reads from all of their meters. Now, to prevent data leakage, we've organized our HDFS directories so that they don't share the same, base directory. Separate customer directories. Other ways of naming things to prevent mixing, but still allow multi-tenancy. So there are. It's something that that can work. I think it's. I don't know how many other big data platforms are built in a way where each customer gets their own big data platform. It would be too hard to scale that way. Yeah. So.
Darren, there's a question on the webinar.
Oh.
What throughput and latency does Hive provide to the platform from the devices to Data Torrent? Have any scalability or performance issues been encountered with respect to Hive?
We have had issues with Hive. We decoupled Hive from our DAGs. So We use Oozie workflows schedulers to insert the data from our Avro files into Hive tables. And so our DAGs they don't fail when Hive as a dependency is suffering. Yeah, but we have had issues with Hive. That's about as much as I want to touch on. Yeah. Thank you.
I also want to take this opportunity to do a shameless plug for Silver Spring, which is we're always hiring. So if you or you know folks who are interested in the IoT space, the smart grid industry, we have a variety of positions open, both in this team, looking at data pipeline stuff, smart streetlights. So as always, if you're interested, come check us out online. Likewise, I mentioned the Starfish initiative, a great chance to get involved if you're interested in cities, smart cities, sensor stuff. As well. It's a great opportunity, so do check us out online.
There's one more question. Do you have a concurrency limit on your platform?
Yeah, that's concurrency limit.
Maybe you can ask for a clarification.
Yeah.
Okay. Just for the benefit of the audience, we also have people online watching this, so it's being telecast. So, you got an answer?
No, I think
We can move on. Okay. Anything else, Greg or Darren? Covered everything? Yeah, that was great. Thank you so much for making it here. And I was just talking to them, and they're based out of Redwood City, so they're a Bay Area headquartered company. But then Greg told me they're moving actually very close to this location, so you're going to be moving to the South Bay. So we'll be neighbors. And thank you for coming today and sharing about your use case and your successes as well as the challenges. I think that was a very candid view of how you use the platform. So if there are there any more questions in the audience or over the webcast? Yeah, absolutely.
Where do you currently implement your cluster? Like the cluster? Where is it implemented?
I'll repeat the question. No, hang on. I just want to repeat for this. So the question was, where do you currently implement your cluster?
We have an in-house data center, as well as an external data center that we use. You want to know the actual location?
Any other questions? Great. So just a quick reminder, if you don't mind filling out the feedback forms or the survey and just let us know any feedback you have or anything else you'd like to hear in the upcoming meetups. And thank you all for coming over today. Thanks so much. Hopefully the traffic has subsided by now, so cuts your travel time back home.